In a previous video, we learned about electronegativity and how when one atom is more electronegative than another, the electrons are more attracted to that atom in a bond. So anytime that you form a bond, anytime you have two nonmetal atoms that are bonded together, it's likely that one of those atoms is going to be more electronegative than the other, really unless you have the same molecule bonded to itself. So in like Br2 or like in F2, certainly one of the fluorines is not more electronegative than the other, and so that bond, those electrons are shared equally between both atoms. Okay, in that case, this bond right here is referred to what's called a non-polar bond. Okay, anytime the electrons are shared equally between both atoms, the bond is nonpolar. However, in most cases, like in HF, one of the atoms, like fluorine, is more electronegative than the other. Okay, and in that case, because fluorine is more electronegative, these electrons that are right here in this bond are more attracted to the fluorine atom than they are to the hydrogen. Okay, and what that does is that creates what's called a polar bond. Okay, and the way that we represent that is we make a little plus sign and then we keep it going over towards the fluorine. Okay, and that thing right there is called a dipole. That's going to become pretty important here in just a minute. Okay, and the reason we write it that way is, number one, we can kind of see that positive sign there. If the electrons are more attracted to the fluorine, which they are, then it gives hydrogen what we call a partial positive charge, and then fluorine a partial negative charge. Okay, and then the arrow obviously is pointing towards the more electronegative element, meaning that the electrons are more attracted to the fluorine than they are to the hydrogen. Okay, and that bond is a polar bond. And again, almost all bonds that are covalent are polar covalent bonds. Okay, so, and because HF only has that one bond, then that molecule is also polar as well. Okay, so here we can see it as well. One of the ways that they represent the partial positive charges and the partial negative charges is with the Greek letter sigma. Kind of looks like that, like an S with a little extra end on it. Okay, and then again, that's that partial negative charge and the partial positive charge. Again, a more typical way is you talk about a dipole where you do the little plus and the arrow pointing that one. Okay, so if a bond has a dipole, then it's polar. If a bond doesn't have a dipole, then it's nonpolar. So in larger molecules, though, what about molecules that have more than one bond? Is we have to consider all of the dipoles. Okay. So in this case, it is possible to have polar bonds, but have the whole molecule be nonpolar. Okay? And for this to happen, then there has to be what's called a dipole moment. Okay? And they use this actually a lot in airplanes. In airplanes, they talk about the moment of the airplane. If one side of the airplane is heavier or has more weight on it than the other side, then the moment isn't zero. The airplane has a moment. Okay, and what that does is it tends to cause the airplane to rotate in one direction. Okay, and then the airplane has to compensate for that. They try to make it so both sides are even, and basically so both sides cancel each other out, so that the airplane also does not have a moment. Okay, same thing here with molecules. Okay. For a molecule to be polar, the dipoles cannot cancel each other out. And by that I mean, look at CO2 right here. You've got a dipole, oxygen's more electronegative, so you've got a dipole going this way, and you've got a dipole going this way. Okay, but because it's a linear molecule, those dipoles cancel each other out. And because they cancel each other out, even though the bonds absolutely are polar, overall the molecule is non-polar. Okay, so for a molecule to be polar, it has to have polar bonds and the dipoles must not cancel out. Okay, one of the words that we use a lot to describe this is the word symmetrical and asymmetrical. And again, go back to the airplane. When I was talking to somebody about this, they used that word. If the mass in the airplane isn't symmetrical, then it will mess up the moment of the airplane. And again, the airplane will still fly, but again, it'll kind of have that tendency to always go to one side or the other, depending on which side has more mass. Okay, so in CO2, again, each dipole is equal and exactly opposite of each other, and therefore they cancel each other out. Okay, so yes, absolutely, this molecule does contain two polar bonds, but because the dipoles cancel, the molecule is overall non-polar. And in this case, we say when a molecule is non-polar, that it has a dipole moment of 0, or it just has no dipole moment. Okay? So that is a non-polar molecule. Okay, let's look at water though. Okay, so first of all, how do I know that is the correct shape of water, by the way? Water is bent, has bond angles that are a little bit less than 109.5 degrees. Okay. Which atom is more electronegative, hydrogen or oxygen? Oxygen, certainly. And so we're going to have a dipole going this way and a dipole going this way. Absolutely. So that's our correct dipoles. Do those dipoles cancel each other out? And the answer is no, they do not. Okay? Because one's going this way, one's going this way. If you kind of average those two together, what do you have? What you really have is you basically have a dipole going like this. Okay, and so therefore this molecule does have a dipole moment, and therefore it is absolutely polar. Okay, and this italicized part is a really how I would say it on a test. Okay, again, think about symmetry of the molecule. A molecule that is symmetrical have dipoles that all cancel each other out and is therefore non-polar. A molecule that's asymmetrical does have an overall dipole moment due to those dipoles that aren't canceling and is therefore polar. Okay? So if somebody were to ask me, is water polar or non-polar? Explain. I would say water is polar. Okay? And then in my explanation, I would say that water is polar because the lone pairs of electrons on that central atom, and that's going to become important here in just a minute, that those lone pairs of electrons create an asymmetrical molecule so that the dipoles don't cancel. And again, what the grader is going to be looking for there is your mention of the symmetry and talking about the fact that the dipoles don't cancel. Okay? That is telling the grader I know what I'm talking about when I'm talking about why a molecule is polar or non-polar. Okay? Now, again, I just said this about if molecules have lone pairs of electrons on the central atom, that's usually a good indicator of, oh, there was a bond there, but we took it away and replaced it with a lone pair. That's usually a really good indicator of is it polar or non-polar. Okay, NH3, I'm just going to draw these real quick. Looks like this. It has a lone pair right here on the nitrogen. NH3 is polar. Okay, SO2 looks like this. Okay, absolutely, SO2 is polar. SEI2 looks like this. Again, I'm not going to put all the dots on iodine. Okay, but it looks like that. Okay, polar. Okay, in general, if there are dots on the central atom, you know that it's polar. And how are you going to explain that? The lone pairs of electrons on the central atom cause the molecule to be asymmetrical, and therefore the dipoles don't cancel. You could say overall it produces a dipole moment, etc. Okay, so example 1. Is NO2 minus polar or non-polar? Explain. You must begin by drawing NO2 minus. So NO2 minus looks exactly like this. Okay, and then once you've drawn it, again, your explanation has to be based on whether the dipoles cancel or not. So notice I underline the important parts here. Your answer should look something like this. NO2 minus is polar because the lone pairs of electrons on the central nitrogen atom create an asymmetrical molecule in which the dipoles do not cancel, giving the molecule an overall dipole moment. And molecules with a dipole moment are polar. Okay? If those two electrons weren't there and there was a double bond there, then absolutely now it's nonpolar. Okay? Now, the other time, so that's very, very common, that when there's dots on the central atom, it's polar. Okay? A lot of times, too, like in CH4, that is a non-polar molecule. All four of those bonds, that's a tetrahedral shape. All four of those bonds cancel each other out. That's a non-polar molecule. Okay? But, and again, this is up here, when you replace one atom for another, if I take one of those hydrogens away, and I put a fluorine there, all of a sudden, you've got a very, very strong dipole going this way, and hydrogen and carbon and hydrogen are pretty similar, actually, in electronegativity. So you have one dipole going way down here, really, really strong dipole, because fluorine's so electronegative. And so that also does make it polar. Okay, typically when you have big, big molecules, such as, let's say, a molecule like this, CH3, CHH, CHH, COOH, versus just CH3. Actually, let's make it just like the other one. Hold on. C double bond to the O, O, H, and H. Okay? In this case, which one's more polar, which one is more non-polar? Okay? In this case, first of all, they're both polar. Okay? And the reason is because, again, notice this part right here is perfectly symmetrical. Just a bunch of carbons with a bunch of hydrogens around it. But then this end right here throws off the symmetry. Okay? Now, so yes, they are both polar. Which one's more polar, though, is this one down here. Okay? So when you get to bigger molecules, notice again, you have a fairly large non-polar region in this molecule, and then you have the polar region at the end. Whereas this molecule here, the whole thing is polar. There's no non-polar region at all. Okay, so once you get to big molecules like this one here, you can look and go, okay, that most of that is nonpolar, and then there's that little polar region at the end. Okay, so that makes this molecule over here less polar than that bottom one. Okay, so PF3 and BF3, the difference between them, and again, I'm going to leave off the dots on the fluorines, is this. Okay. Boron with the 3 fluorines is a trigonal planar shape. PF3 with the 2 dots on the P is a trigonal pyramidal shape. Okay, trigonal planar, no dots on the central atom. That is non-polar. PF3, dots on the central atom, asymmetrical, dipoles don't cancel, polar. Okay, letter B, NO2 plus. NO2 plus looks like this. And O3 looks like this. Okay? And in this case, again, you've got a dipole going this way, you've got a dipole going this way, those dipoles cancel, therefore non-polar. Okay, whereas here, this is a bent shape, even though I drew it linear. Remember, the way you draw it doesn't matter. This one absolutely is a bent shape with angles a little bit less than 120 degrees. Okay, and so therefore that is absolutely a polar molecule. It's asymmetrical, the dipoles don't cancel, etc. Okay, the fact that there's a double bond and a single bond here does not matter because remember resonance structures, it really isn't a double and a single, it's a blend of both of those. Okay, so there isn't a double and a single bond there. There's, remember, like a bond and a half in both places. Okay, letter C is actually similar. I don't want to draw them all again, but letter C is very, very similar to this one right here, where you've got a 3-carbon chain, and then you have a 6-carbon chain. So you've got 3 carbons in a row with an OH at the end, and then again, all the hydrogens on there, and then you've got 6 carbons in a row. 4, 5, 6, again with the OH at the end. Are they both polar? Yes, absolutely. Which one's more polar? Absolutely this one. It's got a relatively small nonpolar region and then the polar region at the end, where this has a much, much larger nonpolar region and then again that polar region at the end. Okay, and then NH3 and H2O. Again, I think we already showed you this one, and then water we already talked about. Okay, this one's important though, because again, which one's more polar? Okay, in this case, you've got one lone pair on here, you've got two lone pairs on here. Okay, the greater, when you have similar structures, because remember, if all of those are bonds, these are both tetrahedrals. Okay, so which one's more polar is the one that has, again, more lone pairs on the central atom, the more asymmetrical that molecule is. This one certainly does have an overall dipole, but again, with those two lone pairs versus just the one here, this one has a larger dipole moment, so this one, water, is more polar due to the greater number of electron pairs, therefore making it more asymmetrical, etc. Okay, example 3, the dipole moment of XeO3F2 molecule shown below is 0. Identify its molecular geometry and explain how its geometry and polarity of its bonds result in a 0 dipole moment. Okay, so first of all, you've got 5 bonds. 5 bonds, no lone pairs. Okay, and again, now you should know that's a trigonal bipyramidal shape where you've got a fluorine sticking up, a fluorine sticking down. What happens to those dipoles? They're equal and opposite. They cancel. That's basically a linear molecule there with the fluorines. Okay, and then the oxygen, again, if you remember this shape, the oxygens basically form a trigonal planar shape. Okay, where again, you've got those dipoles forming 120 degree angles, and they're all canceling each other. Okay, so identify its molecular geometry. Absolutely, trigonal bipyramidal. Okay, the dipoles from the Xe bonds cancel because again, one's going up, one's going down, and from the XeO bonds because you've got that trigonal planar shape, resulting again in a 0 dipole moment for the molecule. Now, in general, what did I say? If there are dots on the central atom, it's going to be polar. And that's a really, really good way to know whether the molecule is polar or not. If there's just one central atom and there's dots on the central atom, in general, it's going to be polar. But there's 2 times when it doesn't, okay, when it's not polar. One of them is when you have a linear molecule. Okay, remember there's 2 linears. If you go back to the chart of all of the shapes, there's 2 different linears. One of the linears is formed when you have, it's actually very similar to this right here, but it's where instead of oxygens on here, we're going to have lone pairs. So 1, 2, 3, 4, 5, 6. Okay, and you've got, again, the dipole of the fluorine going up, the fluorine going down. They cancel. The 3 lone pairs are forming a trigonal planar shape. They also cancel. So this is one time here where that is when there's dots on the central atom and it's non-polar. Okay, the other time, and we can use xenon as well, is one where you've got 4 bonds and 2 lone pairs. Okay, that's where, again, you're forming a square. This is a square planar shape, okay? Square planar. And that square, the fluorines, all those dipoles all cancel out. Okay, and then the lone pair also basically cancels out. That one is also non-polar. So in general, when there's dots on the central atom, it's polar. And you're going to describe that by saying it's asymmetrical, the dipoles don't cancel, creating a dipole moment, blah, blah, blah. Okay? Except when it's a linear molecule with those 3 pairs on the central atom, and when it's square planar with those 2 lone pairs on that central atom. All other times when there's dots on the central atom, it's a polar molecule.